Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to welcome Jiansheng Xiao to MSR today. He is a student of Antonio Torralba's at MIT. He's currently, or going to be beginning his third year. In the past, he's worked with Quan, doing a lot of really interesting work in image-based modeling. He's done, I think, segmentation-based modeling, modeling trees, street-side imagery, modeling 3D buildings. A lot of papers, a lot of good SIGGRAPH papers as well. And then at MIT, he switched courses and now is doing even, well, I don't want to say cooler research, but continuing really great research with Antonio. And just some of the highlights on that, he's one of the creators of the Sun database, which is a really huge database for scene recognition. I think we'll be talking a little bit about that today. And there's another paper, what makes images interesting. I think a lot of people, I know that paper made the rounds here at MSR, and a lot of people are interested in that paper, and he was an author on that as well. And today I think he's going to be talking about his most recent work on scene understanding. Cool.
Thanks, Larry, for introduction. I'm very glad to be here to talk about visual scene understanding. Now let's start by playing a game. I'm going to show you a picture for 200 milliseconds. After that, you are going to tell me what you just saw. So are you ready? Okay. Now we look at the fixation point. The photo is coming. So what did you see? Yes, that's right. It's a park. Obviously, you can understand the general gist of the scene. However, in the view of traditional computer vision, many people believe that grouping the image into meaningful regions and do the segmentation must be the first step of understanding the image. But in the guessing game we just played, I don't think you can segment the image in 200 milliseconds. And object recognition people may come to say that by understanding the image, you also need to know the name of the objects. So this is supposed to be the representation of the result of your recognition system happening in your brain. But do we really know so much about how many ducks are there, or the silhouette and the shapes of the ducks, or even is there a duck at all? By understanding the image, probably this is what we mean, is a park. It's a view of a park. But not all information are understood at the side here. Many people ignore that and they still feed the ducks. So in 1975, Mary Potter demonstrated that a novel picture can be instantly understood by human beings in a very short period of time, and a lot of information has been processed by the brain. So now imagine that one day you become the Superman, and you have the power of teleportation. You can just travel around the world in a few seconds. Yet your human vision system can still process the things very well. You can handle it very well. So I would like to argue that understanding the general gist of which type of category the scene is a key major step in the human visual perception pipeline. For example, you want to understand the whole, know that this is a bathroom and this is a park. Even that you cannot recognize that's my PhD advisor, you are probably fine. So why does it matter for computer science? Imagine that one day we completely solve the AI problem and we can build a robot as capable as a human being. It's probably actually running Microsoft Windows inside. So at the first step, the robot step out of the factory. The robot needs to figure out which scene it is in now. If the robot cannot figure out, now I'm standing in a street and running around that is a playground, it may immediately get killed by a car, probably the Google driverless car. Now, the simplest way to model the scene recognition problem is given a picture, we define a list of scene category, and we do the categorization of the scene category. That's the simplest model that we can imagine. If we want to build a system to classify scene category, we got to get some data to test it. So 10 years ago, two of my collaborators built this 8 scene category data set. And then later, a few more categories are added. And this became the standard benchmark of, of this field, and a lot of progress has been made. So let's see where we are after 10 years of progress. Today, with the best computer algorithm, we can attain 88% accuracy using 100 images as training data. So for human, we can attain 95% accuracy on this data set. So the gap here is very small. If you increase to 200 images, it probably becomes very, very small. So does it mean that we have solved the problem? We already nailed down the scene recognition problem. Now let's look at the data set. It looks like this. It looks very easy to classify because they look all very different. For example, if you just open the file manager and you check the image size of the JPEG file, like the file size, you can figure out for this quite well because most of the time for this has very large file size in JPEG. So we definitely need a better database to evaluate our algorithm and to get more intuition of what are we now. Instead of just collecting a larger database, we want to have a more ambitious goals. Like we want to collect all scene categories. So how many scene categories are there in the world? In the domain of object recognition, people have been some attempt to calculate the number of visual object categories in the world. They took a dictionary and they estimate the total number. So we decided to do the same thing for scenes. We took a dictionary and counted them all, and we go through them one by one of all the words, whether this is a scene name or not. And then we download the image using search engine, using those names as keyword, and we manually clean them up. So let's see what category we have. So in the end, we reached about 900 categories and 130,000 images. Category range from Abby to June. Our scene category sometimes have very subtle difference, like kitchens and kitchenette, or all kind of different kind of kitchens. And also, like sometimes they have very similar function and visual appearance, like airplane cabin and bus interior. Our scene category also try to exhaustively cover all the places that encountered by daily life in human being. We cover both urban, natural, and indoor scene. But it turns out that even with the internet worth of imagery, some categories may not have enough image. So for all the experiments in the following talk, we'll use only 397 categories that have enough image, have more than 100 images per category that we can sample. So the first question we want to address is whether our data set is a good data set, whether it is constructed correctly. So we want to ask whether human can do the scene classification in this task. So we want to ask human to do the 397 alternative false choice. That's a very difficult task. But fortunately, there's very hardworking workers on mechanical Turk. So we pay them 1 cent and present an image and ask them to classify the scene. To help them to classify the scene without going through our 400 categories, we design an over complete hierarchy. Like for this image, when they see that it's indoor, and they can go this part out and they can see that it's home or hotel, and finally they choose, oh, this is a bedroom. So we'll filter out those bad workers, and we have some way to identify them. And at the end, for those good workers, we can attain 98% accuracy on the first level and 68% accuracy on the third level. That means we have 68% accuracy on the 400 category choice. So here are some categories that human can do very well. They do it perfectly, 100% accurate. But human is not always perfectly accurate. For example, in this category, human do really poor. They confuse with something else all the time. The following 2 columns is the most confusing category for those categories. Right, they confuse bear with river and coast. But the conclusion is that human can do it. Our data set has been constructed consistently, and human can get it right 2/3 of the time, despite the huge number of categories, and despite that we only pay them 1 cent. So we also want a good benchmark for the computational methods. But how do things get classified in computer? Definitely, objects play a certain role. Like if you know the object names and you know the layout, you can figure out, you can identify and differentiate those things very well. But that's not always the case. In these three different images, the objects are the same, the layout are totally the same, but the function, and there are different kind of things quite well. For example, if you figure out that you are sitting inside an airplane, you are not going to be able to go to anywhere. But if you are sitting in a conference room, you can just go outside anytime you want. Cognitive science have some study on the ensemble statistic. The major conclusion is that the observer have more accurate representation of the whole thing that they can see rather than individual object. So for example, the observer human being may have better estimation of the average size of the dot rather than the individual size of the dot. So it's also very inspiring in the human vision literature. For example, if you see this, if you see locally, it's all just a right segment or a T-junction. There's nothing interesting at all. But by putting them together, you can see that it's obviously like a tree. But not all information is processed in the brain. For example, I'm going to show you a video, and something is changing in the video. Let's see whether you can identify what is changing. So did you see what has been changed? So I'm going to show you the first frame and the last frame of the video. You can see the door is totally different color, the text disappear, and even here, the whole building changed. But you still feel that, oh, it's very likely to be the same image. So the whole system paralyzed. We get an image, we extract some global feature that may lose some information, but we still try to preserve what we really care about, and we dump it into a classifier, and we train and predict the scene categories. By global feature, it means opposite to local feature. Like local feature, we have an image, we extract a jet of local features like the frequency, the gradient, and all kinds of statistics. And by global feature, we just combine them together in some smart way, and we get a feature. Like this image is likely to be the same, similar with this one rather than this one. So we evaluate a whole list of global features to see how they work in our some database. In this list, there are some baseline like color histogram, tiny image, and there are also some very strong texture feature like the latest one, like the hot feature or sick feature, and self-similarity feature, and the standard G feature in this problem. So for a given feature and kernel, we can imagine that all the images are embedded in some certain feature space. A good feature is the one that allows a classifier, such as a support vector machine, to divide one category from the other. For example, a category may be able to divide forest path with all the others, and divide a living room with all the others. We can also combine all kinds of different features together by trying to make a better algorithm by combining them together. So we can do a linear sum of those features, and we use a technique called multi-kernel combination. It's just simply linear sum of those distances. So let's see what we get. Like with 50 training image per category, and remember that we have 400 category. So we have very low accuracy, like around 5 for some baseline feature, and the best single performing feature is the feature called hot 2 by 2. It's the concatenation of 2 by 2 hot together. So but by combining all of them together using the multi-kernel combination that I just talked about, we get 38% accuracy. But human is 68% accuracy. So let's look at the visualization of the result. For example, airplane cabin, we can predict those images quite correctly, but it also confused with some other image like this one. It looks similar, but it's actually inside a band. And sometimes it makes no sense. Like those, I don't know how they really make sense. And here, art gallery, sometimes they make some mistake like hotel room. This hotel room looks like an art gallery because there's a lot of painting there. Here are a few more examples. Some of the confusion seems very reasonable, like the amusement park with the playground, the courtroom looks like a kitchen, and the hospital room confused with dorm room, and supermarket confused with like shoe shop. Now let's tell, okay.
Just to get a sense the percentages, but how many query images? You said these are all above 100 for each class? So
100 for
50,
training.
So that's roughly like 58 out of 100 images, or are there more query images? For supermarket, when you say 58%, like how many?
Yeah, we'll choose 100 images for training and 100 images for testing. On those 100 testing images, we get 58% accuracy. Cool. Now let's look at the let's take a closer look at the confusion matrix. If we cluster the confusion matrix, we can see that obviously there are two clusters here. Actually, if we read the scene name here, most names here are corresponding to outdoor scene. Most names here are corresponding to indoor scene. Now let's take one example. For example, Samba machine can do 75% accuracy. And they confuse with natural canal for 5% of the time. But human confused with beach. That's slightly more reasonable than confused with natural canal. So we want to look at the how the error made by human mistake. Let's compare that error. Like this is the true category. A human confuse those category mostly with those category. Like they confuse bus interior with the subway interior. With a very simple baseline feature, we confuse mostly with something doesn't make too much sense. But with a better feature, you can see that a bus interior does indeed look a little bit like a jail. But if we combine all the features together and we design the best algorithm, we can see that they're making more sense. The error made by them and by human is very similar. Here are a few more examples. Like the beach confused with coast, and then also if we combine all the features, it's also confused with coast. So we can quantify this phenomenon. Here is a list of features that we evaluate based on their performance. We can see that we are, for each category, we plot how often the most confusing category was the same for human on each feature. So with the better and better feature, we see that the error made by the computer and the human are more likely to be the same. To further compare the human performance with our computational model, here are some categories which human perform both good and computer perform both good. Human are bad, computer are bad. Human are good, computer are bad. But human is not always better. Right? For some category, human can perform worse than computer. Like they cannot figure out a baseball stadium. They may confuse with football stadium. So our computer algorithm is still far worse than human algorithm. So does it mean that it's still too immature to be useful for any real-world application? Probably not. In the second part of my talk, I will show that scene understanding seems to be quite mature enough for real-world application in certain domains. I will quickly demonstrate the result on semantic segmentation on street view image, and I will also quickly showcase a few applications for scene understanding. Now the scenario is that we have a camera mounted on a car, and the car drives along with the street. Because the car can only drive on the street, we know that the image capture must be a street scene. That's all known. Now we also know that the camera is facing towards the street side. It's not facing on the direction of the car. With all this given, then the task is to segment the image into meaningful area with the semantic meaning, like this is a building, and this is a tree, and this is ground, this is sky. So to tackle this task, we propose a very simple algorithm. We take a picture like this. For each local patch, we extract some very local feature or weak feature, which may include the response from image filter bank, the 2D pixel location, and the point density and surface orientation as schematic from the 3D point cloud, because we can run structural from motion algorithm on it and get a 3D point cloud, because we have many sequence of image rather than one image. So all these features are helpful, but the information provided are very limited. For example, if we just look at if a pixel is okay on the top of the image, then from the histogram we know that it's either a sky or a building. There's not likely to be anything else. So if we combine all these weight features together to form a local feature vector, and we put them into a classifier to train for the category and predict for the category. We can also enforce the spatial consistency. Like an image, like if two pixels are next to each other in the image, they are very likely to have the same label. So we construct a Markov-Langdon field, which is a general technique for enforcing spatial consistency inside an image. We can also enforce the temporal consistency. For example, two images next by, they have many correspondence, like this car, not really. Like some part of the image may correspond to the another part. So we can make a larger graph by linking the subgraph from each individual image. With such a simple technique, we can already attain pretty good results. Here is the visualization. On the left is the image captured by Google Street View capturing car. On the right is the segmentation result. On the bottom is the color-coded meaning of those colors. We can see the results are pretty accurate and robust. Despite that, Google only allowed to give us some super low resolution image while they have something better. So for general semantic segmentation of the general scene, I have to say that the problem is very difficult. Some progress have been made. For example, the Microsoft research group in Cambridge in UK. But the problem itself is very difficult. In our case, because we only focus on straight scene and the capturing environment, and everything is very constrained. So the problem suddenly becomes easier. After we published this work, a few groups in other universities also follow it, and they get very similar results or even better results. But furthermore, if we have a better image quality and also the 3D laser scan of the street, we can add a laser scanner on the car, then we probably can get much better result to narrow this problem down. I'm very glad to see that many companies have realized this opportunity, and they have started to design systems that produce better results and with some very interesting application. One interesting application is Google's driverless car. Essentially, it's doing something very similar, like in real time, but by combining multiple sensors and do some tempo tracking of the moving object. But the ideas are very similar. Another interesting application is building reconstruction. If we figure out which area of the image corresponding to a building, we can reconstructing properly. Here's a system that we built to automatically reconstruct building model. We use the Google Street View image, and we run structure from motion to get all the camera pose 3D point cloud. After that, we run our simple semantic segmentation pipeline to attempt the segmentation. Now we detect the vertical lines, and then we have defined some heuristic to segment the building into facade base, because we have huge amount of data. By this way, we divide and conquer the problem, and we can focus one facade each time. But even you make an error here, the algorithm can still figure out that if you merge two facades together. Now with each facade, we combine all the 3D information from multiple view image. And we use a technique that we propose called inverse orthographic composition to compose all the evidence. And we have the composed dash map and the composed textual map. After that, we do a facade segmentation to segment all different areas and fit rectangle to those areas to enforce the architectural regularity. Otherwise, the depth map may be quite noisy and the result may look funny. Now we have a model for each facade, and when we combine them together, we can get the building model for the whole city. Here are the rendering result of the downtown Pittsburgh. we can see the building reconstruction is very robust and may be ready to deploy massively at city scale. Thanks to the semantic segmentation pipeline, that is a trick here. Even you make the 3D algorithm, the 3D still may fail. Like for example, you have a building full of glass, they're highly reflective, you never get good 3D there. But as long as you can figure out the outline from the semantic segmentation, you can just figure a plane there and you can look very visually pleasing.
Do you think you could actually do some additional reasoning about figuring out what are windows, doors, etc.?
Yeah. Some people are doing that, yeah.
Okay.
They can add like grammar and semantic meaning there.
Yeah.
Another interesting application is to predict how memorable an image is. When we browse a magazine or when we browse the internet, we are continually being exposed to thousands of photographs. But humans are not only very good at understanding thousands of images at the same time, at a very short period of time, but also remembering them. But not all images are the same in memory. Some of them stick to our mind, the other get forgotten. For example, in these 4 images shown here, this image and this image are very likely to be remembered, while this landscape image and the house is likely to get forgotten. So we characterize image memorability by the probability that an observer will detect a repetition of a photograph a few minutes later after he sees the photo for the first time. We design a memorability game. So in the game, the participant will view a sequence of images for each for 1 second, and then they have a break for 1.4 seconds. And the task is to press the space key whenever they see an identical repetition of what they see before. So by this, we can get a set of images that are memorable and forgettable. For example, here is a set of images that are very likely to be memorable, and here is a set of images that are very likely to be forgettable. We can observe that most images, if we browse through the data set, we can see that most images memorable must contain a human. And they may be likely like indoor static scene, or may have some funny objects that you never seldomly encounter. And those forgettable images, most of them are landscape. So we can use the image feature that we evaluated before to try to predict the image memorability. We evaluate a whole list of features, and the conclusion is that by combining all the features together, we actually get the consistency behind the prediction of computer and human is very close to the consistency between different groups of humans. Like at the top is the computer can even better than human consistency. So here are some visualization of the image that predicted to be most memorable. You can see they all contain humans.
Did you have, was one of your features, does the human exist in the image? Or is it just in?
It also have some high-level feature, like you use label me to annotate the object and have the name.
Okay, so you have object labels as well.
Yeah, it's right here.
Okay.
And without object, it's like all global feature is the blue line here.
Okay, so it helps a lot to have object labels and.
Yeah, but not absolutely. In the paper, we also plot that if we only have the object and scene, if we only have the object, it's not that much. So the major conclusion is the human consistency is quite high, so memorability is measurable. But computer is also very good at figure out the consistency between humans, so we can do the prediction quite well. So here are some images with typical memorability. Like sometimes they have humans, sometimes they are not, but most of them have interesting story. But these images are predicted to have least memorable, like they are most forgettable, in other words. So most of them are landscape photos. So if you want to let people remember your photo, don't take landscape. So another interesting application is to extrapolate an image. Like I talked about, given an image like this, you know that it's a theater. But not only that, human can figure out this is inside a typical theater, but the camera is facing towards the seat. It's not facing towards the stage. So in a typical theater like this, the layout of the theater like this, you have the stage here, the camera should point from upward. So we are able to build a model, again, using those global features to predict the score on the viewpoint. Here is a visualization of score. You have the highest score in this direction. That means the model can predict the viewing direction for the image. So now we can superpose the input image on the average image of the panorama of theater. So we can see that here looks like a stage, and here is the seat, and the picture can align quite well. And here is the nearest neighbor from the training set. Like you can put the image here, and you can see that the boundary is changing naturally. Now we are going to show some initial result of this boundary extension. The image you first see in the center is the input image, and those parts are the extrapolation result. And here is another example. The extrapolated view is produced using texture synthesis technique by using the nearest neighbor from the training example as the prior to guide the texture synthesis. Here another example. You can actually see that even you see this, you can see that a TV is likely to be here.
Why are these big ellipses all over the place? Is that somehow how you're splatting in? I keep seeing circles everywhere.
Yeah, it's like maybe our algorithm is still not very good.
But there must be something in your algorithm that prefers elliptical regions in a radial direction. Can you explain why those things look like that? Did you see what I'm talking about?
Yeah. I think because it matches it locally. If we do it like pixel by pixel, you have a patch and we match the one pixel at a time. Probably have some bias.
Are your patches circular in some sort of a spherical map, and then when you unwrap the spherical map into a perspective projection, they become elliptical?
Yeah, it can be. Yeah, good point. Very good point. But besides potential like computer graphic application for this type of extrapolation, it also gives us a sense of the boundary extension in human visual system. The boundary extension is an area of commission in which humans confidently feel that they're seeing a surrounding area of the image while they are not actually presented to them. Like if you see a train here, if I ask you to draw a picture of the train, you are likely to draw it slightly larger than the actual view after you've seen the picture. Here's another extrapolation result of the wolf. So in summary, the first part of the talk, I have presented the Sun database, which covers an exhaustive set of scene categories. And we saw that when hundreds of categories become available, for the first time, we are able to evaluate scene classification algorithms realistically. And we evaluate numerous state-of-the-art algorithms, and we establish new bound of computer performance by combining them together. And we also compare them with the human performance. So in the second part of the talk, I saw that scene understanding seems to be mature enough for some real-world application in certain domains, such as the semantic segmentation of street view image. I also showcased several possible applications for scene understanding, including 3D reconstruction of building mesh model, prediction of how memorable an image is, and extrapolation of image beyond its boundary. So last but not least, I would like to acknowledge the effort from my major collaborator and thank all funding agencies provide financial support, including Microsoft. And I also want to thank Gary for inviting me here to MSR and looking forward to some interesting discussion. And you may also go to my website to know more detail about these projects. And if you have any questions, I can take them now. Thank you very much. Thank you.
Additional questions? One question I had was,
you mentioned before, when you do scene recognition, there's a big conflict in my head whether it's important to recognize the objects before you can do scene recognition. Because the first example that you gave us was a park, right? And you said what was in it, and a lot of us said ducks or lake, that sort of thing, right? And we did actually do object recognition. Do you think it's actually possible to do scene recognition without recognizing the objects?
Well, I feel it's like opposite. You need to do scene recognition first, and then the scene recognition can guide the fixation points to search for the object. Because for now, the object detection is that you do the sliding window, you try all possibility. That's super computational expensive. I don't believe that human brain can do that. So what I believe is you recognize the scene. For example, you are looking for a pen, so you look at the layout of space, and you feel that a pen is likely to be roughly here, and then you start to search for the pen. So it's like, let me show you.
Well, in the lake example, though, we were able to recognize the objects without moving our eyes, without searching.
What do you mean by?
Like we recognized the grass, lake, ducks, etc., without moving our eyes, because it was just flashing in front of our faces. So we can do recognition of objects really quickly. So it's a question of, does the scene recognize it go immediately to the pixels, or does it actually take the objects that you can recognize and then use
Yeah, it can be a feedback loop, but different people have quite different. What I feel is that you got to get a picture like this, you got to recognize the scene, you know the layout, and you know how to navigate, and then you figure out the fixation. Like in the room, you're ready to looking for a chair to sit, and then you have the object recognition pipeline going on. But definitely there are some feedback that they're happening very fast and very likely to be parallel. But I feel that this is a case that people have a lot of focus on fixation point, prediction like in human vision literature, and object classification and detection in computer vision literature. But still they are missing this part. Like, by focusing here, probably it will benefit all of them.
Second speaker again.
Thank you.